All right, so thank you very much for attending my talk. In this talk, I'm going to discuss how we actually empower reverse engineering using the latest techniques in machine learning as well as data mining. So the overall process that we try to optimize is about binary analysis or program analysis. So we start with, typically we start with a binary file, which is the sequence of 0, 1, 0, 0, 1. And then we have a disassembler. We can get a list of assembly functions. And each function basically is a list of assembly instructions. And then here is our reverse engineering fellow. And he or she will try to do a manual analysis task to take a look at the functionality or abstract high-level logics of the assembly functions. And depending on what kind of task, such as the malware analysis or vulnerability analysis, so they are different, they have different purpose here. But the overall process, this is the overall simplified process of the workflow, the reverse engineering workflow that we try to optimize. Of course, we have different kind of techniques that here and there helping out this process as well, but we really focus on the last steps here for reverse engineering by trying to answer two specific questions. So when a reverse engineer tries to understand a specific functions, well, we try to address the information needs of the reverse engineering task. Is this something that has been analyzed before by himself or herself, or is something that has been analyzed just a couple seconds ago by his or her teammates, or is just known library functions or a variation of the known library functions? We try to address this information needs, by using an information retrieval approach. So we developed an open source assembly code clone search engine, Camino. And so suppose it's like a centralized repository of assembly language that people can build different repositories, just like on GitHub. Instead of a repository of source code, they create a repository of assembly code depending on the task that they're working on. And then reverse engineers as a team or within organizations, so they can index the assembly functions that they're analyzing, and they can search for the clones as well. So by using this high-level system, we try to address the information needs for the reverse engineering. But when we talk about information retrieval, we need to define what is exactly similarity, right? What is exactly the clone? So in the literature of assembly language clone search, so there are typically three different types of clones. So the first type of clone is an exact clone, right? So there's nothing fancy here. They are exactly the same. So to find this kind of clone, we can simply do exact hashing, right? And the second type of clone is called a syntactically equivalent. So these two pieces of assembly code looks different, but they are actually corresponding to the same logics, but maybe due to different compilers or different versions of the compiler, they use different register or different offsets on the stack to represent different variable. So after normalizing the assembly code, or normalizing the instructions and variable into their abstract high-level token representation, they are actually the same, just like two minifigures here is that the picture is taken from different angle, that's why they're different, but if we normalize the camera, they will be the same. So this kind of clone stat is not difficult to handle as well. And the third type of clone is the minor modification. So for minor modification means that we allow a certain degree of update or change to the assembly code. So this can be done through any like fuzzy hashing or locality-centered hashing algorithms for nearest neighbor clone search. But what is more challenging is that we also have different kind of obfuscation as well as optimization techniques that make the same assembly functions that look completely different. So for example, in this case, suppose the minifigures that on the left-hand side is the original one. We can break it into different parts, reorganize it, and even inject different noise to it. So the image here looks very different. So how does this translate to a real-life scenario? So here we have four different assembly functions. They actually come from the same source code. So the one that on the left is the original one that without any optimization. And then the second one is with the all the optimizations turns on. And the third one is obfuscated by the control flow graph flattening techniques in the OLLVM. So all the basic blocks are break into different parts and duplicated and arranged by a big switch, gigantic switch. And the last one is obfuscated by the bogus control flow. So because we are trying to do a search engines, right? So to find this kind of code, one possible way is that to do dynamic analysis, right? We can run the program because they're the same thing, so should expect the same input and output behavior. But as a search engine, we cannot really able to afford the luxury of dynamic analysis. So we don't want the user to wait for, let's say, 10 minutes for the query to dynamically execute it or symbolically execute it. So we look into the existing literature or existing methods to statically model the assembly code. So we identify two main challenges or problems. So typically when we try to model assembly code, the relationships among the tokens that's within the assembly code is mostly neglected. So for example, we have XMM0 register versus the other streaming operations. They're not exactly the same, but I mean, they on high level, they focus on same aspect of the assembly instructions. Or fclose and versus fopens, they're different, but they kind of corresponding both to the file operations. And string compare and mem compare, string copy and memory copy, sometimes they are swappable, right? And the second challenge, the second problem is that it's about how we weight this information. So as an experienced reverse engineer, you may not actually read every single line of assembly instructions when you try to analyze something, right? So reverse engineering look for something interesting. So we put higher weight on something that we never saw before that violates what we commonly know. And regular, random, repeated patterns are not interesting, so we want to put a lower weight on that. So these two problems actually quite similar to the problems in natural language processing using machine learning. So actually what we're trying to do is that, well, we try to build a neural network to help us to address these two challenges. But before we jump into how we build this neural network for assembly language, I want to talk about how I learn English. As most of you can already tell, so I'm not a native English speaker, so my first language is not English. The way that I learned English is that it's quite brutal. We do a lot of multiple choice correction in exams. They're trying to complete a sentence with different options, right? So to find the right word to fit into the context or the syntax of the sentence, right? So this is how I did before, and it turns out okay, so I can speak English right now. And 10 years later, people find out that this is a fantastic way to train a neural network to learn human language. So given the neural network, so we asked the neural network to solve millions of these kind of multiple choice questions following the same way. So in this case, first we need to have the questions, right? So let's say if I have some text, a sequence of text that cat set on the map, so we apply a sliding window on the text and ask the neural network to predict what is in the middle, which is set given the context. So you can see here, the input is the cat on, and the output is set, right? So we want the neural network to make these kind of predictions over all the questions. And this approach turned out to be great. We can learn actually very rich semantic relationship between tokens from the natural language. So you can see that one typical example is that the representation of king minus man plus woman actually is queen, and the bad minus good, and it's maniacal killer. It actually kind of makes sense, right? And the paragraph vectors here actually can capture what is unique about this question. Suppose you always said the cat sit on the mat, the cat sit on the mat, but one time I told you that you make a wrong answer. The right answer is not set, is speaking. And then you'll be okay. So the exam that I took last week actually has a very weird correct answer that is not said is about speaking, right? So this information is captured on the paragraph ID, which is like the exam ID, right? You record it in a specific exam, there's a weird answer. Well, we're following the same way, applying this model, and directly on the assembly code, it works great. But the problem is that assembly language is not like text, it's that linear layout, right? So we adopt this model a little bit. So instead of asking the model to predict what is in the middle of the token, we ask the model to reconstruct the instruction, the assembly instruction in the middle by considering the neighborhood instructions, right? So given a sliding window over the assembly instructions, let's say a size of 3, I ask the model to predict, reconstruct what is in the middle by taking the context, the neighbor instruction into considerations. And this model, it turns out, it works pretty well on assembly language, and by visualizing the relationship among the assembly token, the tokens that we saw from assembly language is quite interesting. So we can see that on the vector space, 60 bits register. So the register pretty much group into different bit lengths. They kind of be similar to each other considering their context. And then the drum operations are grouped together. We also have the condition operations that group it together. And if you look into the function calls, the C library, the libc function calls inside the code, we can also find that 5 operations are grouped together, as well as the networking and access control functions are very similar to each other. So these are the token under the call instruction, right? After the call instruction. So also we have the memory operations that tend to be grouped together, as well as string search, and for all the math related function calls are also grouped together, but that is not shown in this slide. And we conduct the Chrome search evaluations by comparing the original binary against the optimized one, and then we compare our approach with all different kinds of a static approach, including graph-based, assembly code, like assembly language-based, as well as 2 most recent dynamic analysis-based approach. It turns out the approach is pretty accurate in matching between the original one as well as the optimized one, even compared to the some recent dynamic approach. But we don't have enough samples to make a conclusion that is a statistically significant difference. And then we also conduct the Chrome search analysis using the OLLVM obfuscator. It's not the best out there, but it already makes the assembly code looks very different. And it also turns out that our approach performs very well on this for this obfuscator. We also conduct case studies on vulnerability retrieval data sets. It's like you have a repository of different assembly functions. Some of them are vulnerabilities. We try to retrieve them. And compared to ESH, which relies on dynamic analysis, our approach without any modification actually have a 0 false positive. And as a static approach, it takes only a couple milliseconds, like a couple hundred milliseconds to get the results. And we take another extreme, we use the Tigris obfuscator, which rely on virtualizations, just-in-time executions to obfuscate the assembly language, assembly code. And so for the encode-retro obfuscation, well, it performs great. For virtualization, we can still recover some of the vulnerabilities. For JAT execution, well, still recover some of them. But if we apply all of them, like you apply the encode-retro and then virtualization, and then we apply the JIT execution. Unfortunately, we cannot recover anything because it looks already very, very different. So for this model, for this approach, we developed to push the boundary of static analysis against code obfuscation and optimization. So even performs somewhat better than the recent dynamic approach. As a static approach, efficient, scalable, we can just use it for our search engines. But the problem is that, well, when we present a Chrome, because it's a vector representation, right? It's very difficult to explain to the end user, to the reverse engineer, that why exactly these 2 functions are considered as a clone, unlike in the other subgraph-based clone search method. But I mean, after obfuscation, the graph boundary is broken anyway, so the subgraph, the concept of a subgraph is no longer valid. Static approach, of course, has some inherent disadvantage. So there's no, it cannot recognize, for example, the dynamic jump table. And we also assume the assembly code coming from the same family. So we are talking from searching English against English, but not English against French, right? So it's not like x86 against the ARM code. And actually, we put this model as part of our Camino binary analysis platform. So it's on GitHub, it's open source, it's ready to use. It can be deployed on your laptop, on your workstation, or you can deploy it on the cloud services, relying on Spark. So it's ready to use. Besides of Asm2Vec, which focus on optimization and obfuscation, we also have ASM clone, which is the typical subgraph clone search approach that given the query, given a target, we can identify the clone this subgraph. It's like really showing the reverse engineering, which part of the function is a clone to another function. And we also have a Semino module, which search for the cross architecture assembly instructions. So you can search x86 against the ARM code. So this approach actually we rely on the intermediate representation for the code matching. And this is also following a subgraph clone search approach. So it has a very good degree of interpretability for search engines. So that's it. Okay, so any questions?
Any questions from the audience? Please come to the microphone, and before you ask questions, please state your name and affiliation, please. Thanks.
Hi, Taesung Lee from IBM.
Hi.
I'm not sure if you had any discussion about the different architectures, different neural network architectures. For higher level languages, like Java, I think people have used LSTMs or CNNs. And actually, CNN has been also used for binary. So have you compared them with this CBOL structure?
So the reason why we use a more simpler architecture is that we want a higher throughput rate of the training model, because we want the model to learn as much as from the data. So that's why we didn't rely on LSTM. So another reason why we don't use LSTM is that we observe that when we increase the context, the larger the context we increase, the higher chance that you can actually just directly predict out the assembly instruction that as our target, and it will have less information propagate back to the exam ID that we can remember. Oh, it's like make the question extremely difficult for the model. So instead, we make a lot of simple questions to the model. So actually, we did try our LSTM on our own, but the performance is not very good because the throughput rate is very small, compared to.
Thank you.
Yeah, thank you.
All right, due to the time limit, we may only take one question for this talk. So let's thank Stephen one more time.
Okay, thank you.